Okay, I think this is a good one. Kind of more interesting than some of the stuff that we've looked at before. It's actually something new. So first thing I talked about was that there's this idea of separation by continuous functions. So we've been looking at separation, and before this, the way that we've been separating things is by open sets. And that's kind of like what you expect a standard thing in topology to be. Two things are separated if you can get open sets, disjoint open. First off, you've got to start off with two disjoint things, and they can be separated if they can be enclosed in disjoint open sets. Okay, so kind of another way of separating things, and it's a stronger way, is by using a continuous function. So, so we have two subsets of a topological space. Oh, that should be an X. Where did B come from? If there's a continuous function from X to the unit interval, such that the function is 0 on A and 1 on B, then we can say that A and B can be separated by that continuous function. More strictly then, if not only FA equals 0, but F inverse of 0 equals A and F inverse of 1 equals B, then A and B can be precisely separated by a continuous function. So the fact that it's the unit interval here is nothing special. Of course, we can replace it by any closed interval, and we can even replace it with R. So in different books, you'll see different definitions. So any sets that can be separated by a function can also be separated by open sets and by closed sets, right? Because you just look at the pre-image of 0 to a third, for instance, or 0 to a quarter or whatever, pull that back, that's going to cover A, then 3/4 to 1, pull that back, and that's going to cover B, and the closures of those are also going to cover them as well. So you can do that. So there's kind of obvious reasons why things can't be separated by functions. So for example, this half open interval and this half open interval can't be separated by a continuous function, right? Because a continuous function would have to, whatever value f of 1 was, you'd have to agree with that. So you can't get a continuous function separating those two things. Other things to note, of course, is only closed sets can be precisely separated, of course, because this is a closed set, the pre-image is going to be a closed set. But just because two sets are closed and separated by a continuous function does not mean that they can be precisely separated. See examples of that later. So this is Urysohn's Lemma, which is the highlight of today. This is by Pavel Urysohn, who was, I mentioned before, he's part of that sort of Soviet school that really forged ahead with topology in the 1920s. And he tragically drowned when he was young in Brittany, and supposedly that's something topologists do, is they go to a pilgrimage to his grave in Brittany, France, to do real topologists. So yeah, he was at Moscow State University, so He was a graduate student there and then was an assistant professor. And he did other things besides this. We're going to see his thing about metric spaces. And he and Alexandrov were the ones who came up with the idea for what compactness should be. So he was a really bright and upcoming person. Okay, so Urysohn's lemma basically says that the thing that makes normal spaces a right thing to do is because they have enough continuous functions. And in particular, they have enough continuous functions so that you can separate out closed subsets. So if you've got a normal space, which remember means that disjoint closed subsets can be separated by open sets. If it's a normal space, then we can separate them by a continuous function. And we can pause for a moment. You've got to think, where on earth is this continuous function going to come from? Because we've got nothing, it seems, right? But we've just got enough. So the outline of the proof is we construct a family of open sets indexed by the rational numbers with the property that the closure of U of P is contained in U of Q whenever P is less than Q. And this is the part where we need the spaces to be normal. Then it's very straightforward. After we do step one, to extend this to a family indexed by all rational numbers, to use that then to define our function that we need, and then to show that f is the desired function. Okay? So all this is pretty straightforward. So it's number one, which is really kind of like the special thing here, which is, and this is the really bright idea. So we've got A and B as our closed sets in our space X. And so since B is closed, we're going to let U1 be everything which in X which is not B. Okay, now since X is normal, we can separate A and B by open sets. And so the set that we use to separate A from B, we're going to let that be U0. And because it's separated from B, the closure of U0 is not going to intersect with B. Right? So the closure of U0 is going to be entirely contained within U1. Okay, so even though I've done this blue and this red, all this is still U1. So everything's U1 except B, and then U0 is just this open set that we've got here. Oh, in fact, U0 includes A, so of course it covers A. Now we want to put a set between U0 and U1. Okay, well first we're going to use the rational numbers, and of course the rational numbers in 0, 1 have two really good properties. One, they're countable. So we're going to do some kind of induction to do our sets. And secondly, they're dense. And that's going to turn out to be why the whole process, why the continuous function works. Okay, so P is countable. And let's just range P then in an infinite sequence, starting with 1 and 0, which we've already just done. And a standard way to do that is just by going through the denominators. So we just go in, I guess it's kind of like some kind of dictionary order on the denominator and then the numerator. So these two things have the same denominator, so this goes first because it's got a lower numerator. So if we go through, do that, that then puts out all the rational numbers. So there's two orders here, right? There's the order in the sequence where we're counting them, and then there's the order in the normal sense, which number is bigger or less than the other ones. Okay, so we define U1, we define U0, so let's define it for the next number in the sequence, which is a half, so we want to do U1/2. So again, we just use normality. So we can find then, we can then put an open set between U0 and kind of B here. So U1/2 contains the closure of U0, right? Because that's going to be so the sets we're using normality on is the closure of U0 and B. Because of that, we can then stick in an open set to cover the closure of U0. And since it's a disjoint from some open set which is covering B, the closure of U1/2 does not intersect B, so it's going to lie within U1. Let's do it again. So we just do it again. So the next thing is a third. A third is the number after a half. And so we're going to put it between U0 and U1/2. Okay. Now, so what do we do? So now what we're doing, we're using normality. And so what we're going to use normality on is the set U0 and the complement of U1/2. Right, we're doing U0 because that lies, so U1/3 is going to lie between U0 and U1/2. So we're going to use the closure of U0 and I guess the closure of U1/2. Okay, so we can find then our U1/3, which is going to be the set that covers the closure of U0. So the closure of U0 is going to be within U1/3, but then the closure of U1/3 is not going to impinge into U1/2 because we've used normality to do that. How far do I go? I can't remember how many colors I did. Okay, the next thing is U2/3. Okay, now 2/3, we want that between a half and 1. And so that means we've got to use normality of X on two closed sets. And the closed sets we're going to use is going to be the closure of U1/2 and B. And so that's our two closed sets that we're between. And so U and 2/3 is going to cover the closure of U1/2. And the closure of U and 2/3 is going to lie within U1 because it's not going to meet B. Okay, and so we just keep on going, right? So we can put in U1/4 between U0 and U and 1/3. We can put U and 3/4 between U1/2. No, between U and 2/3 and U1. And then here's U and 1/5 between U0 and U1/4. And so what happens in general? Okay, so we've got, if we let Pn be the first n rational numbers in the sequence. So notice we could have used a different sequence, of course. And in fact, we don't need to use the rational numbers. We could use any countable dense set. So let's say for the first n rational numbers, we've found our UI for each of those. And let's R be the next number in the sequence. Okay, and so we're going to be able to put that between two numbers in the actual order, right? The actual order of the rational numbers, right? Because 0 and 1 have already been accounted for, and that's always going to be the minimum element of our set, and 1 is always going to be the maximum element of the set. We're always going to be able to find two rational numbers that occurred before it, and that's going to be the immediate predecessor and the immediate successor. Right. So if those numbers are P and Q, that means the sets UP and UQ have already been defined, and so therefore, by the normality of X, we can find our UR such that our two closed sets that we don't want to get to close to is the closure of UP and the closure of UQ. With the proviso that if Q equals 1, it's actually B they're talking about. And so, for example, here, this is the 9th step in the process. We want to find U and 2/5. So we want to put it between U and 1/3 and U and 1/2. And by normality, we can do that because we're just going to contain U and 1/3, and we've just got to avoid U and 1/2. So we can just keep on doing this. And that was Urysohn's bright idea. And so how can we turn this then? Oh, first we've got to extend it to all the rational numbers. And that's pretty straightforward. So we just let, if it's a negative rational number, we let UP be the empty set. And if P is bigger than 1, we just let it be the whole set. And we still have, right, that if P is less than Q, then the closure of UP is contained in UQ. Right? All we've got to worry about, because we've set it up that way with the numbers between 0 and 1, well, if P is negative, this is empty, that's always going to be containment of what's over here. And if Q is bigger than 1, then this is going to be the whole set, and of course that contains everything else. So it extends all the way. So that means we've got a collection of sets parameterized by the rational numbers, which covers the whole set X, and we have this nice property here. The closure of UP is contained in UQ whenever P is less than Q. How do we turn this into a function? Well, given any point in the space, we let Q of X be the set of rational points such that the open set UP contains X. Okay, so for example, if we go back here, in here, we've got 1. Here's 3/4 and 1. Here it's 2/3, 3/4 and 1. 1/2, 2/3, 3/4, 1, etc. So as we go in towards A, we're getting more and more sets that we're covering. Okay, so the set is bounded below because it contains no number less than 0. Because remember that the UPs where the P was negative was the empty set. And it contains every rational number greater than 1. Again, because by our definition, we had that if P is a rational number greater than 1, then it's the whole set X. Okay. So because of this, we've got a set which is bounded below and whose greatest lower bound is a point in 0, 1. So that's our function. So we're just going to define f of x to be the inf of the p's such that x is in u of p. And so why does this work? So remember what we want it to do. We want it to be a continuous function, which is 0 on A and 1 on B. Well, the last two things are pretty straightforward, right? If x is in A, then x is in UP for all p greater than or equal to 0. Again, just go ahead and look at our thing here. Actually, everything within the red space here, right, is going to be in all the UPs for p greater than 0. So f of x is 0 for x in B, x in A. What happens if x is in B? Well, if we go back and look at it again, B is in U1, but for any rational number less than 1, all the UPs are over here. So none of them contain B, and of course, all the rational number, actually, it's not even in U1, right? That's right. U1 is x minus B. But every UP with p greater than 1 covers B because UP is all of x in that situation there. But if it's in every UP where p is bigger than 1, then the inf is 1. So f of x equals 1 if x is in B. And then continuity is the only one really thing that we need a moment to think about. But the way we've set it up, continuity comes straightforward because if x is in the closure of UR, then f of x has to be less than or equal to R, right? Because Q of that point there contains all the rational numbers greater than R. And if x is not in some UR, then f of x has to be greater than or equal to R, because again, because that set of QX contains no rational numbers less than R. Okay, so what do we have to do to show continuity? We just have to show that an open set gets pulled back to an open set. Okay, so if we've got x in our space, f of x is going to be some number between 0 and 1. So let's put it into some open interval CD. Again, by the I guess here is where we need the denseness of Q. We can find rational numbers such that we can put f of x naught actually between P and Q. And so by these two statements there, x naught itself has to be in UQ minus the closure of UP. Right, so if we go back here, it has to lie in some kind of strip like this. And further, the image of this has to lie within this CD, this interval here, because P and Q are between C and D, again by 3 and 4. And that's all we need to do to show that F is continuous. So it really is, I think, a really nice theorem. It's just kind of amazing how we just kind of came up with its real function from kind of nowhere. So notice we can't improve it to get precise separation without further conditions, right? Because, for example, this red area here, anything in there, f of that is going to be 0. And everything in the blue region here, f of that is going to be 1. So it's not precisely separated. So we need more things to be able to make it work. And we actually know spaces where we can't do that. So, for example, we know that this space here, from the last example, we know that this is a normal space, but it's not completely normal, right? Since that we found a subspace of it which wasn't itself normal. So completely normal, remember, means that all subspaces have to be normal. And this space here, the closure of this, whatever it's called, the minimal uncountable well-ordered set, the closure of that is completely normal, because every subset of it is normal, but it's not perfectly normal, which means that it can be precisely separated. And of course, the trouble comes if you look at the singleton of the uncountable, that minimal uncountable element. It's not G delta, and in the homework you're going to see why that means it's not perfectly normal. So remember, normal was T4, completely normal was T5, perfectly normal was T6. Metric spaces, though, we can get precise separation because we've got the metric, and that gives us a really nice continuous function. And so, for example, if you define the function f of x being the distance from our point to A divided by the sum of the distance from x to A to x to B, that gives a function which is going to be continuous, right? Because it nowhere vanishes, because if A and B are disjoint, then this number is going to be non-zero. And if x is in A, then the distance is going to be 0. So the function is going to be 0. And if x is in B, is this right? Oh yes, if x is in B, then this is going to be 0. So this is going to be 1. Right, so it's a 0 and A and 0 and 1. But more to the point, it's actually precisely if x is not in A, this is going to be some non-zero element here, non-zero number, so you're going to get a number bigger than 0. And if x is not in B, And this is going to be a little bit bigger than the distance from x to a, and so it's going to be strictly less than 1. So this function gives us a precise separation of closed sets. The next thing to notice is that you can't use this proof on regular spaces. Right? So you can't separate, in a regular space, you can't always separate a disjoint point from a closed set. And the reason is, you can do this step 1, right? If A is a point, you can get a U0 around it, but it fails at the next step, right? Because now you've got to deal with U0, and so now you've got closed sets. And so that necessarily doesn't mean that you can find open sets that surround them. So regularity can't be extended to complete regularity. And so that's why we have that definition. So a space is completely regular, called T3.5, because that's between regular and normal, if it's T1, and you can get a continuous function to separate a point from a closed set that doesn't contain that point. And so it really is T3.5 because there are spaces that are regular but not completely regular. I'll show you an example of the one that is, but it's so contrived I don't want to go into the full details of it. And we've already seen spaces that are completely regular but not normal. For example, the Sorgenfrey and oh, that's supposed to be closure there. They're completely regular. We've already seen that they're not normal, but they are completely regular. The next theorem will show you that they're completely regular. So here is this example of regular but not completely regular, which I started going through, but it's just so complicated and involved and so contrived. So let S just be the upper half plane of the real plane. Let P be the point 0, -1, and our space, which is regular but not completely regular, is T, which is this half plane union with that point. Okay, and so here we introduce a whole bunch of sets. This is kind of like a vertical slice, a diagonal slice, and the union of those two. On the next slide, I show you pictures of what they look like. So here's the topology on this space here. So the things which are properly in the upper half plane, singletons are open sets, so it's almost discrete. For points on the x-axis, open sets are this vertical slice union with this diagonal slice. It only goes up to 2, right? Subtracted some finite set. Okay. And for P, the basic open set then is P union with this set N, which is kind of like half of the half plane. So everything which is like in this sort of quadrant sort of thing there. Okay, and well, I didn't do that correctly. So it turns out this is a regular space, but you have problems. You can't separate by a continuous function a point on here, a rational point on here, from the set of irrational points. So, right, it's because it's almost discrete, right? Because the way that it's set up, because if these are open sets, then the open sets basically along the x-axis, it's also discrete. So it just it's so artificial and contrived. I didn't really want to go into all the details, but that's the kind of thing to do. Because what happens is if you assume that you had such a function, it turns out the function, if the function is zero at infinitely many points, then it's basically zero. It has to be zero everywhere. So you can't get a continuous function to separate the things out. So that's enough of that. But completely regular spaces are really nice. Because in the sense that a subspace of a completely regular space is completely regular, and a product of completely regular spaces is completely regular, as distinct from normal. And so this is why these spaces here are completely regular, because what was it? RL is normal, and the closure of S infinity is normal. So therefore they have to be completely regular, so their product has to be completely regular. And the proofs aren't that difficult. Okay, so why is a subspace of completely regular subspace completely regular? Okay, so let's say we have a point in a subspace of a completely regular completely regular space X, and let A be a closed set of Y of the subspace, which is disjoint from X naught. So the obvious thing we have to do is transfer everything to the regular space, and we can do that, right? So if A is a closed set of Y, then A has to equal the closure of A in X intersected with Y. So that means this point X naught can't be in the closure of A in X. So that means since X is completely regular, we can find a continuous function that separates X naught and the closure of A in X. And then you just restrict that function to Y. And that will separate X naught and A in Y. Right, because f of X naught equals 0 or 1, or whichever one you've got 0 and 1. And it's also going to work when we go to Y. That's straightforward. What about products? Okay. So if we have a point of a product of completely regular spaces, and let's say we have a closed set of another typo, that should be let A be a closed set of the product of those X alphas disjoint from our point X. Okay, so if we choose a basis element containing X, since A is closed, we can have it that this basis element doesn't intersect that closed set. But we're in the product topology, right? So this neighborhood, this basis element has to be mainly X alphas, except for finitely many. Okay, we'll let this be the indices of those elements of the basis element which aren't the whole space. It's only finitely many. Okay, now we use the fact that the spaces are completely regular. So for each of them, for each I, we can find a continuous function fi that separates the elements at alpha I from x alpha I minus u alpha I, right? So since this is an open set, this is a closed set, this is a non. So these two things are separate, so we can separate them by a continuous function. So we can do that in x alpha I. Now we're going to transfer everything to the product space. And so we do that by using the projection. So let phi I be the composition of fi with the projection there. Right. So then this phi is going to be a map from the product space to our interval. And then we just let f of x, the function that we want, just equal the product. Just multiply all those functions together. And that's going to separate x from this, from the product space minus that basis element. And A, of course, is in here. And the thing is, what happens? So it's only going to equal. Remember, each one of these things is between 0 and 1. So it's only going to equal 1 if all of them equal 1. Let's say that's the x. And it's going to equal 0 if any of them equal 0, and that's going to be in this space over here. So that works. And so it's the fact that we're only multiplying finitely many of them together that makes this work. Of course, if we were infinitely many, who knows what the product would be. I think that's it for the day. Okay.